So welcome you all. In this video we will be deriving the kinetic energy of a rod which is rotating about one of its endpoint. Okay, so what our target is, this is a rod and it is rotating. This is the axis of rotation. What is the orientation of the axis of rotation? It is perpendicular to the plane of this board. And what is the plane of the rotation of the rod? This is the board plane, and the rod is rotating like this. I hope the rotation is clear to you. Now let's say the rod is rotating with an angular speed of omega, and the total mass is given to be m, and the total length is L. That is, from this point to this point the length is L and the total mass is m. One more thing, this is a uniform rod. What is the meaning of uniform rod? Uniform mass distribution, that is mass per unit length is a constant. Okay, because for non-uniform rod the derivation is different. For uniform mass derivation is different. Now I hope what is the actually first point which must come to your mind is, at this moment how many points are there in the rod? The points are infinite. Okay, like for example 1, 2, 3, 4 and infinite points are there. Each point is moving with a different velocity. How different? Because this point, how do we calculate the velocity, the tangential velocity in a rotational motion? We simply multiply omega with the distance from the axis of rotation. So this point will be moving with velocity omega into L, because this distance is L. Now what about this point? Let's say this is the midpoint. So this will be the velocity, and the velocity will be equal to what? Omega into L by 2. So similarly the velocity variation is linear. Okay, like for example every point in this rod will be moving with velocities in increasing order. And how many points are there? Infinite points. What is the size of those points? Infinitesimally small. Okay, so this diagram was just to explain what is actually happening. Now what is our aim? We have to find the kinetic energy. This is our aim. Okay, now what will be the rotation? This type of rotation will be there. I mean, what will be the path of this point? This will be revolving like this, or this will be going into a circular motion. Similarly this point will be moving in this circle, this point will be moving in this circle. The circles are getting smaller. So that is just an imagination. Now our target is to find the kinetic energy of the rod. Now as I told you, the number of points in the rod is infinite. What type of quantity is kinetic energy? It is a scalar quantity. So what I can do is, I can find the kinetic energy of a single point and add all those points, all the kinetic energies of these points. So basically what will be involved? Integration, because the number of points are infinite. So rather than summing up those points, we will be doing what? Integration. Why did I mention scalar quantity? Because it can be added directly. Kinetic energy is a scalar quantity, so kinetic energy of all these points can be integrated or summated. Now I am rubbing these arrows which I just drew to show you the imagination. Okay, so let me rub this. Now this is anti-clockwise rotation with a speed of omega. Now I should rub this. Now let us consider a small portion. I have drawn it large, but it is a very small, infinitesimally small part of the rod. Let us consider the length as dl, infinitely small length dl, and mass will also be very small, that is infinitesimally small, denoted by dm. Now let me consider the distance from the axis of rotation to be small l. So we have a point of length dl, mass dm, distance L from the center. Now this point is moving with velocity what? Omega into small l. Omega into small l. Now let us first find the kinetic energy of this portion. I will denote it by dk. dke, either dke or simply dk. Why dk? Because the element is very small, so the kinetic energy associated with this element will also be very small, infinitesimally small. So dk will be what? Half m, that is dm, into velocity square. Now what is the velocity? Omega l. Omega l square. Sorry, this would be small l. Yeah. Now what did I say before? I will have to integrate it to get the kinetic energy of the complete rod. So I will be doing the integration. Okay. Actually, when the number of points are infinite, we cannot sum it up. We will have to integrate it. Okay. So that is the use of integration in physics. Now dk becomes k. Half is a constant, can be taken out from the integral. What is left? dm and omega l whole square. It will become omega square l square. Omega is a constant because rod is moving with angular speed omega, so omega is a constant which is given in the question. Okay, so omega square is a constant, so can be taken out from the integral omega square. Now what is left with us? L square. Now is this integration possible? No. Why isn't it possible? Because we have two variables here. One is small l and second is m, dm. But to complete an integration, I will have to write this dm in terms of dl. Then only I will be able to integrate this term. So I will try to write dm in terms of dl. How? Let me draw it here. What is dm? dm can be written as simply linear mass density into the length. What is linear mass density? Total mass by total length represented by lambda. So dm into length is what? dl. Now what is lambda? Linear mass density will be m by l and dl. So what we got? Relation between dm and dl, that is representation of dm in terms of dl. So I will replace this dm with this term here. Okay, so k will become 1 by 2 omega square. dm is what? m by l dl, and here is l square. Now again m by l is a constant, so can be taken out from the integration. It will become k is equal to 1 by 2 omega square m by l. What is left? dl into l square. Now it is very simple. It will become half omega square m by l. What is the integration of l square? Simply l cube upon 3. So l cube upon 3. Now it is a definite integration. I will have to put the limits. Now why I am doing a definite integration here? Because what is the purpose of integrating here? I want to cover this, all the points from this point to this point, and for this point what is the distance from the axis of rotation? 0. So that means for this point this L will become what? 0, and for this point the length will become capital L. So to cover each and every point of the rod, I will have to vary the length L from 0 to capital L. So what will be the limits? 0 to L. Okay, so I think I have almost completed the integration. What will it become? 1 by 2 omega square m by L, and this will become L cube upon 3. What will be left? L and L cube. L square will be left. So due to lack of space I am writing here. It will become half omega square ml square. Now this 2 into 3 will become what? 6. So this is 6. This is our answer. This is what? Kinetic energy of a uniform rod of mass m and length l, which is rotating about the end point, about one of its end point. Okay, so this is our final answer. So I hope the explanation was complete and clear, and I think I am able to say what I wanted to say. Thank you so much.